好，那我这边也开始录音了。欢迎大家来到今天的演讲。那我是今天演讲的主持人许蓝天，目前在德国攻读博士。那按照惯例，我们先会简单的介绍一下 Terra 是一个怎么样的组织。稍等一下哦。那 Project Terra 它的全名呢是 Taiwanese Young Researcher Association，宗旨呢是要串联世界各地台湾各个领域的学术人才。那我们现在呢会每周会有学术演讲，就是各位今天所参与的这个目的呢是鼓励领域内的知识交流，还有跨领域的学习。那我们也会办学界、业界的职涯经验分享。那今年呢，在9月还有11月，还有各有3场还有总共3场的演讲，待会我会给出更多的资讯。我们也会有学长姐来辅导台湾同学申请海外研究所。那这个部分大家可以持续关注我们 MMP 的 program。像我刚刚所说，从研究所申请到各领域或是跨领域的学术交流，到毕业之后寻找职位的经验分享，Tara 都期望能成为各位这一路以来的好伙伴。那 Tara 刚开始是从一群物理系的学生创立的，那到现在呢已经成立了7年。在这期间呢，我们也陆续增加了各个领域的会员以及讲者。那从物理到工程到生医到社会科学，我们也有越来越多的会员还有讲者。那也非常欢迎各位成为我们的会员，然后呢来到 Terra 给出你的 talk。那在目前为止，我们已经办了200多场的演讲。那在 MMP，也就是我刚刚所提到的海外研究所申请的这个 program 呢，也已经辅导了超过600位的导师。那如果你的身边有需要这项帮助的研究生呢，也欢迎你分享这项资讯给他们。借此机会呢，我也顺便广告一下近期的活动。那在2024年呢，Terra 迎来了6场职涯讲座，那时间已经进行到一半了，我们现在还有3场，在9月跟11月，主要呢会分享在欧洲、在美国、在学界、在业界或甚至是跨学业界的经验分享，那也欢迎大家来参加。相信听到这里呢，你已经对 Terra 产生一定的兴趣。那如果你想要持续追踪、掌握最新的讯息呢，欢迎你追踪我们的社交平台。那小帮手会在 Chat 上面贴上链接。那事不宜迟，我们先来介绍一下今天的讲者许瑞福。瑞福呢，在台湾电机系获得学士学位之后呢，在台大电信工程学获得硕士学位，目前在该所攻读博士。他的研究领域有天线小型化、多铁天线、机械天线等。因为瑞福的卓越的研究表现呢，他获得红海教育基金会2024年的科技奖。除了学术上的努力呢，他也积极致力于改善台湾的高教环境，倡导博士薪资资讯制度化等。在此之前，他也曾担任台大研究生协会和 IEEE 台大学生分会的主席。今天瑞福带来的演讲是多铁性材料于 GHz 频段天线微型化的应用开发。那演讲跟回答呢，总共会是1个多小时。那让我们欢迎瑞福。
感谢主持人的介绍。然后，等一下啊，我换另外一个档案，不好意思。这个这样看得到。
可以，但是不是全荧幕。
现在是全荧幕，
嗯，
还是我跳出去
哦，
再播？
对对，是的，好，现在是
哦，
全荧幕。
好好。Okay, so uh, Today I will present my topic in English, and maybe later if we discuss you feel comfortable with Chinese questions, it's okay for me because it's also easier for me. So my topic is regarding multiferroic materials for antenna application at gigahertz band. And right now I'm PhD candidate, so hopefully I should be able to graduate soon. Hopefully, yeah. And this topic is uh, very interesting to me, but it's also a bit difficult because it's a multidisciplinary across perhaps material science, mechanical engineering, and electrical engineering. So in the right-hand side, the picture that I will talk about and our main focus today is about the small antenna problem. So yeah, thanks to the host introduction. So I graduated from electrical engineering. So my background is more for double E and antenna engineering, and I spent quite a few times trying to read more literature on material science. And it's kind of a different word to me, but I try to learn that to uh, have spend more time studying this topic. And recently, I submit to this technology award, and it's open for actually also for foreign researchers. So quite a few students from foreign study overseas also awarded with this scholarship. So maybe if you are interested, you can also apply for that. And also, it's kind of my tiny side project that I used to be the president of Graduate Student Association, participate some of the policy making for the PhD student. But now I'm spend more time focusing on my research to graduate student. And my publication list. So the first journal paper that I published last year on applied physics later, that is also my main focus today. And I'm the first author, and my collaborator mostly from UCLA, the Professor Candler, and two PhD students now graduated. One work at Sandia Laboratory, and the other one is highly related to this topic. She is the first one to give a comprehensive numerical result for the idea of multiferroic antenna, Jackie, and she's also one of our co-authors and some conference papers. And currently, I also have another paper that is under review on IEEE TAP for more theoretical paper. So here is my outline today. There are fifth part that I will first talk about why electrical small antenna matters, talk about the practical application and problem of that. And there's a long history for this electrical small antenna or ESA's problem, and quite a few pioneering theoretical work on that, and the conventional techniques that has been used by engineers and commonly used to improve their performance. And my main research topic to use multiferroic material to see the potential to improve the performance of small antenna. So to begin with, this is a news, but not so recent. 2 years ago on IEEE Spectrum, uh, they report that the U.S. agency announced a challenge funding and to call for the proposal that hope some people can perhaps break the limit for the small antenna performance. So, and also like a DARPA, they also announced a project funding to look for, it's called Amoeba program, to look for the solution to improve the mechanical low frequency transmitter. So this meter communication that it has been kind of studied over the years, but still a lot, some new proposal call for creative project to have more progress on this topic. So its definition is quite simple and straightforward. So electrical small antenna, or ESA, can be defined by imaginary sphere, and that sphere can enclose your antenna structure. And this sphere, the radius A multiplied by the wave number. Wave number is the your electromagnetic wavelengths, then wave number. And so this Ka is called electrical size or electrical length that can define your antenna. So if this Ka value is much smaller than 1, perhaps 0.1 or smaller, then we call it electrically small antenna. And the small antenna face a similar problem that trigger researchers' attention, and people are interested in that. It seems they all have a common issue. So typical antenna design, you will have some kind of a trade-off between different quantities, like you want the highest gain or wider bandwidth or better efficiency that can radiate more power, or you want a smaller size. But over the years, people notice that when you shrink down the antenna size, most this performance will inevitably degrade. Like you almost doesn't radiate, or the bandwidth is very narrow. So it's kind of a more general problem, not just to optimize your design. It's kind of a physical common problem. And why this problem is important for several applications, like I mentioned earlier, if you want to utilize low frequency communications, you will inevitably face these issues. For example, if you want to have a signal transmit at around 300 kilohertz, then your wavelength over free space is around 1 kilometer. You cannot imagine that it's an easy job to build a 1 kilometer antenna to transmit your signal. It costs too much, and also maintenance is a problem. But there are several communication scenarios that require this kind of low frequency, like on the battlefield, or if you utilize the ionosphere reflection or some ground wave transmit your signal, or you want to penetrate your signal under seawater, ground earth. All these application that is not so common, but critical for meter applications. You need to use a low frequency signal to do that. So that's one of the main drive that military communication call for project and research on electrically small antenna. So to give an example, it's a public information that I found online. It's called very low frequency transmitter. It has a huge area and very high power consumption, and very tall to transmit a very low frequency to have a simple Morse code communication. So it's some photos that can found online. It's over the whole peninsula to have an antenna array, and I find some photos from Google Map. So it's almost across the whole peninsula. So you can imagine that the maintenance for this kind of low frequency transmitting antenna is very hard to imagine. And so there's a strong motivation for they to improve the performance. And for more close to our life, it's personal electronics. For example, we are interested in wearable device or some IoT applications, or people are discussing that more in-body biomedical devices. For example, if something can implant it around the neurons to monitor the neuron activity, or the something can be swallowed and to take recording or pictures for your biological activities, or even inside the cellular cell signal monitoring. So all these applications, although it's more close to commercial applications, it requires extremely small feature size. So in this case, might also face the problem of electrically small antenna. So I will introduce a little bit some of the electrical small antenna theory that has been built and quite interesting. So the different researchers think of a common problem, as I mentioned before. It seems like it's a general fundamental problem. So is there a way to formulate antenna size and all these performance metrics? So why do we need a theory? It's kind of several reasons that we always want a kind of a golden standard to pursue the best performance. It's kind of all engineers want to do that. And some people might say, okay, I designed this kind of antenna that has groundbreaking performance. So perhaps it's unphysical, so that we need to have a common base to discuss that. Also, we can facilitate our fundamental understanding what is antenna doing. And some of the discussion is helpful for guidelines to design antennas. So to formulate this antenna limit, there's a common and famous limit called Wheeler-Dew limit or Dew limit. So it basically saying that your quality factor will be limited by your electrical size. So if you have Ka value that is very small, like 0.1, 0.1, then you will have this third order term that will dominate. Then your quality factor will be very high. And quality factor is very high, basically just means your antenna probably doesn't radiate. You will have a very narrow bandwidth. So this kind of very old theory, a lot of antenna researchers work on that. I mainly reference to this textbook, and I will pick up some of the interesting and pioneering one that I share with you. So the very first paper around, it's published in 1947. The Wheeler, he is the first author to establish the link between antenna size, bandwidth, and efficiency. So he observed that small antenna is kind of have a far field pattern very similar to a capacitor or a inductor. So he start with this ideal capacitor and inductor that he can calculate the radiation performance and the stored energy so that he can link quality factor and antenna. And very soon later, there's a very famous scientist called Zhu Lancheng, and he is the first author to have mathematically derived absolute lower bound on quality factor of a small antenna. And he gave a very general definition of a small antenna, which is a imaginary sphere that can enclose your antenna structure called GHz-sphere. So if you are interested, you can look at it's old papers, but still very interesting to study. So basically, that paper, he's dealing with a fundamental mode spherical wave function solution to your Maxwell equation, and then he reformulate into an equivalent circuit network. Then this equivalent circuit network, he makes several assumptions that it is an ideal Jew antenna, that there's no conduction loss or no inner stored energy. And he discussed this ideal antenna that has best possible achievable quality factor. So based on that equivalent circuit, he can derive this kind of a figure that here it's the same as a Ka. So you can notice that for the fundamental there are several conclusions in that paper. One is that if you radiate at fundamental mode, it's more efficient, that quality factor is lower. And when you decrease your antenna sphere or antenna size, your no matter at which mode, your quality factor will increase a lot, so that the radiation performance is weaker. So when this limit is very general ideal limit is proposed, and a lot of researchers follow this work, like they try to improve this limit to make it more more practical, not so ideal, to give us some modification. Or some people use a more concise and general method. He solved for the Maxwell field equation. So he derived the electric field equation and then calculate the propagating and non-propagating energy, so that he can define analytically correct quality factor lower bound. And some of the more recent work, they also extend this kind of a definition to bandwidth, because in antenna design, you also care about how the bandwidth or the impedance matching has been designed with your circuit. So they try to derive the maximum bandwidth that can be achievable and to link that to your antenna performance. So this paper is also quite worth reading by Professor Stephen Piper, published in 2012. So basically, it's very hard to experimentally prove that this lower bound is right, unless you can build a record high, and you need to be fit the definition. So his method is quite interesting, that he filter out all published paper on transaction antenna, IEEE Explorer and transaction TAP, and to build some common basis. And so for all this published literature, he tried to compare, and if they follow the ideal choose limit or not. So the x-axis is the electrical size, which is Ka, but the y-axis here is a little bit different. It's a bandwidth efficiency product. So you can understand that previously people care about quality factor, but the issues is that if the quality factor is very low, you have a wide bandwidth. Sometimes it does not imply that your antenna can radiate efficiently. Very likely that some of the losses, like in your substrate or other losses source, consume your radiation power. So if you want kind of a absolute performance limit or metrics for your antenna, the bandwidth multiply efficiency, called bandwidth efficiency product, is more general. And so in this picture, you can notice that as it goes to 0.1, the literature will, previous work will slowly deviate and maybe even lower than this ideal bound. And although there's a point, seems like it breaks the record, but there's a definition issue that they have a different bandwidth calculation. So it's discussed in the journal, and it's not actually break the limit. So now we know that, okay, electrical small antenna have a theoretical, perhaps cannot be break the limit. And so we hope for design our antenna maybe closer and closer to this limit. Still, we can get more radiation from that. So the commonly used techniques to improve that, there are several ways. For example, you can use a high permittivity or permeability material that can decrease your electrical size. But the problem is that you will store more energy. So it's kind of a trade-off. You shrink down your antenna, but the quality factor or bandwidth may be sacrificed. Or you can modify and optimize your geometry that we'll give some example later. Or people use a lump component. So lump component refers to some circuit component that is contrast to your microwave circuit will relate to your electrical length. So the size might be bigger, or some other advanced method to do that. So for some shaping that has been used, for example, you can put some slot in your antenna structure so that at the same size, you can effectively increase your electrical size. So although you doesn't change your overall size, but still you have your current path longer. So you can radiate with a smaller feature size, or you can bend your antenna structure to save your space, or to do some meander line or the fractal network. So all of this technique is kind of a similar concept, is that you try to more efficiently, more possibly use your antenna sphere or Joule sphere as efficiently as possible. And some other example that I try to find more closer to our daily life, like Apple Watch Series 4. If you tear down and you can find it online for each component part, you require very compact size with communication band like LTE or GPS or Wi-Fi. So like some antenna engineers try to base on this Apple Watch shape to design a antenna. For example, in this paper, they design a full multi-band resonance to have a GPS, Wi-Fi, and 5G applications. And all of the memo is based on the half wavelength. So it's not rigorously an electrical small antenna, and still it has acceptable performance. So what I observe is that I think currently the strongest drive for this study still from metered applications, but some of the interesting applications might be might have potential, especially in biomedical applications that require extremely small size, but still at the commercial application band. So now I will talk about my research and some of the interesting conclusion that I would be happy to hear some questions or ideas from you. So recently, antenna community, they start to discuss a new concept. It's called mechanical antenna. So if we start from a very simple idea, is that we learn from the dipole antenna to have a acceleration, deceleration, then you will have a radiation. So what if this kind of a current source is not driven by your voltage, but mechanical force? So theoretically, it works because we just need, from Maxwell equation, we just need a time varying field to have a radiation. It does not require the source from voltage or mechanical force. So we might have a radiation from conventional one like conduction current, metallic antenna, or we can just have a time varying magnetic field like a spinning magnet, or it's a dual part that from the electrical field, the charge holder electret microphone, or it came from the material that has time varying magnetization or electrical polarization. So in this chart, I haven't updated recently, but I think most of the important work that I read recently, I try to summarize like a different mechanism, different geometry, or different frequency band. So you can notice that even until now, I think like 90% of the work on this topic is still focused on the low frequency. and only one work. And also, I will present my work that has been demonstrated above gigahertz range. And this work, I will talk about that later. So there are several figures that I show, like people develop a pendulum array. It's a permanent magnet and use that as a transmitter to communicate, or permanent magnet. And in this work, they also already transmit the can be encoded and decoded messages, or use a magnetoelectric or multiferroic material to transmit the signal, or simply it's a very strong piezoelectric rod, and this resonator can use as a transmitter. And it's a team from Stanford, and the one that we'll mainly talk about, it's a magnetoelectric resonator that has been demonstrated at around 2.5 gigahertz. So I've for the definition of multiferroic material and magnetoelectric material, I follow from this paper from Nature. So multiferroic sounds unfamiliar, but it's kind of intuitive. So as long as your material possess 2 or 3 ferric properties, like you combine the ferroelectricity, ferromagnetism, or that is rarely used ferroelasticity, then it's called multiferroic. And another term that has been used often, but it's kind of a more general, it's called magnetoelectric coupling. So it just simply describes that if you have a magnetic field or electrical field, that can have influence for the corresponding part. Like a magnetic field can alter the electric polarization, or electrical field can alter your magnetization. Then we call it a magnetoelectric coupling. So magnetoelectric coupling is kind of a general, since it does not require that your material is necessarily ferric or not. And people will try to achieve that in multi-layer composite material to have a stronger coupling. So for example, you can use a strand, your material strand, and to couple between different phases. So it's called two-phase material. So it's also a long history for this kind of a material, but more recently, people it's kind of a long history, and people always look for the opportunity for this practical application for this kind of a material, like this recent Nature review paper, electrical engineering. He give a timeline for that. So it's this 2017. It's a 2.5 gigahertz antenna team review paper. And yeah, I published after that, so we are probably here, probably. So in that review paper, it gives several application scenarios. So people commonly use a magnetoelectric material to have application in memory or logic, and to control the unit, or some magnetometer, kind of a magnetic field sensor that can test extremely low magnetic field change. And the antenna is more recently and more rare. And some energy harvesting or tunable component. Tunable component, like if you alter your magnetic field, then like your frequency band, like a filter or phase shifter, you can control your frequency by your external field, or some non-reciprocal RF device like isolator, limiter, or circulator that also been discussed. Use some magnetic material or magnetoelectric material. So for my focus on my research, the motivation for use of multiferroic material, we already talked about the electrical small antenna has almost doesn't radiate. So there are some fundamental issues for that. So if you start from Maxwell equation, you know that conventional antenna use a conduction current to radiate. So if we can try to avoid this ohmic loss, and we don't use the conduction current, we simply use a time varying magnetic field as a radiation source. Perhaps we have opportunity to further improve the performance. So the basic concept is that to have an electrical field, then you will create a strength change. Then this strength change will have an effect for your magnetostrictive material that will drive your magnetization to radiate. And the additional benefit is that your antenna size now is not decided by your electrical length, the conduction current part. Instead, its resonant frequency is mainly decided by your mechanical resonator, which is decided mainly by the thickness of the membrane. So it's around micrometer at gigahertz range. And this animation that I copied from my friend Sedan, and he gave it it's understandable. So first you have a resonance for your structure from the electrical field. Then this strength field will drive your magnetization or small magnetic dipole inside your material. And this time varying field can generate your EM radiation. So for this concept that people has been working recently, I think uh, uh, until now, this most comprehensive and perhaps most comprehensive work for the theoretical part is this paper. So she tried to solve for the LLG micromagnetic equations and Maxwell equations and also the Hooke's law for your mechanical motion. And in this paper they solve it's a three-dimensional FDTD solver, and also all of this equation is fully coupled to be solved. So in this journal paper, she has several important conclusions. So she demonstrated that at the left-hand side, and in time domain, you will have the stress field with a alternating sinusoidal amplitude. And when she turn on the coupling turn in the magnetostrictive layer, then you will slightly decay, indicating that some loss or radiation might be generated. And she also calculated the far field pattern it's very similar to a dipole pattern. And several important conclusion is that radiation efficiency can be maximized with the condition that your bulk acoustic resonance frequency is overlap with your ferromagnetic resonance, so that for the disturbance inside your material can drive your magnetic spin or your small magnetic dipole most efficiently. So there are several theoretical predictions. I think that is important for this topic is that you need to align your FMR resonance and Bose resonance by adjusting the external bias field, and you need to reduce your loss turn and to align both resonance to maximize your radiation. So for this work, the experimental proof or similar work for this is that, and I think there are several issues has not been done, and that will relate it to my research. So for their work, they demonstrate a 2.5 gigahertz thin film resonator to measure their radiation. But of course, so far, one of the motivation is that most work focus on kHz and megahertz range. And but the problem is that you can notice that here the S21 transmitting coefficient performance, they only compare the structure from aluminum nitride and to the Magnetostrictive material and to the simple aluminum metals. And I think if we want to investigate the radiation mechanism more carefully, some detailed study should be done. And also one part of our work. And also their measurement setup information is limited. So it's not easy to understand. So I think at least two things should be further tested, also presented in my journal paper. The first is that when your external biostatic magnetic field, uh, this biostatic magnetic field in his work is mainly examined in megahertz range, but what we care more about the gigahertz range, which is the main innovative point in his work. So it remains unknown that your bias field, how can that affect your coupling performance in gigahertz range? And the second thing is that we need to be more careful, especially it's an electrically small antenna. What is the maybe only a primary contributor to this radiation? Which part or which layer of material that is actually radiating is important. So that connect to my work. So I have I have designed and fabricated similar structure. The difference is that they use a Bach mode, but here I use a lateral electrode and to generate a shear wave. But the material and structure being used is similar. So it's a microscope photos for our device that is assembled through a bond wire and PCB. So you will have some device cut from silicon die and looks like this, and to have a narrowband resonance. So I put that in an echo chamber to do the measurement. So I connect with my device with a VNA to have a transmitting distance at least larger than radiating near field. And we collect our signal from a linearly polarized home antenna. And before doing this experiment, we also carefully calibrate everything and to test what's the noise level for under this setup. So when we make sure the noise level fits our calculation and we start to connect to our component to do the measurement, and it requires additional microwave absorber to make sure there are no multiple reflection between them. So we try a lot of times and we found that now the narrowband signal, narrowband resonance, mechanical resonance indeed have enhancement for your transmitting coefficient at both band. So we are happy when the first time doing this experiment. This fits our prediction and understanding. That's good. But next things, there are several things that confuse me a lot until today. So we has fabricated some more samples. Like we have a larger size resonator, increase the radius from 200 micrometer to 500 micrometer. So we test different devices and we alter, which is also a main argument in our paper, is that the central layer or the middle layer nickel, which is a magnetostrictive material, it possesses the magnetoelastic coupling. According to theory, should be the main radiation source turn. So we alternate this layer, or kept everything the same except this layer, and alter that into a permalloy, which is 80% nickel, 20% iron, uh, mixed mixed metals. And this kind of permalloy is famous for one of the properties that there's very, very tiny, almost close to zero magnetoelastic coupling. So it's a very good reference to check that if the magnetoelastic coupling is the only and primary term that can generate your radiation, because you kept everything the same except this layer. And this layer should be accordingly does not have this coupling to drive your radiation. And we also do some EDAS to check the atomic composition. Make sure post fabrication this ratio is correct and reasonable. So what confuses us is that at the lower band, okay, we first look at this result. Previously, we have a 200 micrometer smaller resonator with a nickel, has a corresponding radiation, good. And 500 micrometer have a close resonance around this frequency, which is reasonable because it's mainly decided by thickness, and also have an enhancement, good. But here comes the problem. Our dummy device that is made of permalloy should not have a radiation, but we also have similar properties. Okay, now we can explain this behavior. And the other thing, what is much more strange, is that this resonator, as you can notice previously, it has two narrow band, one at around 3.5 GHz, a second around 6 GHz. And the nickel turn, okay, it's reasonable because we all have radiation enhancement. But this time, the permalloy not just have a radiation enhancement, it absorbs the energy, and part of our energy transmitting disappears. So you have a gain drop. And that confuses more. So now we still need to move on. So okay, maybe we can check some more experiment. So what we trying is that we put our test piece under the static magnetic field. So we put that bias field at the implant direction because the implant direction is more easily magnetized. That can be saturated easily. So our setup looks something like this. We record our static magnetic field first, and then to record the reflection coefficient correspondingly for each test piece. And we notice now it's all reasonable behaviors. So for the lower frequency band, the 200 micrometer nickel and 500 micrometer nickel, the reflection coefficient have a kind of a absorption change according to our change of external bias magnetic field. And our permalloy case stay almost perfectly with each other. It just doesn't respond to the bias magnetic field, static bias magnetic field. And for the higher frequency resonance, it also shows coherent behavior. In nickel, it correspond to the bias field, and in permalloy, it almost stay the same. So if we plot this behavior in our applied bias field at low frequency band, you notice a similar behavior from nickel. It might be that first you overcome the coerced field, and later it gradually saturate. And permalloy just does not respond to the static magnetic field. And the higher frequency resonance shows similar behavior, but the magnitude is much weaker. So we have three conclusions, but I think these three conclusions cannot be seen as an answer to these questions. So it's an ongoing research that I still have a new project trying to do in to answer this question. So first conclusion is that since we only alternate or replace this magnetoelastic or magnetostrictive layer with non-magnetoelastic one, this reversal definitely, of course, just correlated to this replacing or alternating behavior. And second conclusion is that suppose we are using non-magnetoelastic turn and non-magnetoelastic material to check the radiation, we still see the similar behavior and of course another weird absorption behavior. So we cannot have a solid conclusion that this so-called magnetoelectric radiation is, as we thought before, theoretically is determined mainly by magnetoelastic effect. And the bias field is static external bias field is more reasonable. Permalloy is immune to the variant bias field, very clearly opposed to the nickel case, and which fits more correspondingly to previous theory. So at this stage or moment, we think the low frequency or more close to DC magnetic field can fit the theory perfectly. But if the radiation comes from the gigahertz range, that might have some unsolved issues should be addressed. And thank you for listening. And I hope this is interesting. And I'm still doing the research for this topic. So any opinions and questions are welcome. Thank you.
谢谢瑞福的演讲。那我们的直播跟录影都还在继续。那如果有人有问题的话，欢迎提出。有人有想问的问题吗？我们也可以先把录影跟直播关掉。那大家有想问问题，或者是大家就可以开你的打开你的 camera，然后我们也可以做 networking。那我们现在。